Last year, the global automotive market crossed a major threshold. Every single week, consumers were buying 250,000 electric vehicles. But scaling up production to meet that global demand hits a stubborn physical roadblock. The lithium-ion battery is the single biggest contributor to both the cost and the weight of the vehicle. And there is a serious safety concern baked into those heavy cells: thermal runaway. If internal temperatures spike unexpectedly, these batteries can fail, catch fire, or even explode in a rapid chain reaction. Historically, solving a chemical flaw like this meant relying on physical trial and error. That slow, expensive laboratory process simply cannot move fast enough to keep pace with the automotive industry's production quotas. To fix the hardware, researchers are turning to software. Developing the perfect battery is now a massive data problem, and artificial intelligence is providing the required processing speed to solve it. To understand how this works, we have to zoom all the way down to the atomic level. At IBM's Almaden Research Lab, scientists are hunting for completely new electrolyte materials to build a better battery from scratch. This illustrates the AI foundation models used by researchers. Pre-trained on 90 million molecules, the AI learns chemistry's structural rules. Instead of months in a lab, deep search algorithms run countless simulations to instantly suggest new, optimized electrolyte materials. By refining these specific formulations, researchers can design batteries that charge significantly faster and pack a much higher energy density into the exact same space. Solving the chemistry directly shrinks the battery's physical footprint. A smaller power source means a lighter vehicle, demanding less energy to move down the road. Zooming out, we reach the physical hardware. Electric vehicles rely on hundreds of individual cylindrical cells closely packed into modules to form the battery pack. Because of this density, if thermal runaway occurs in just a single cell, the surrounding cells heat up exponentially. That localized failure easily cascades into a chain reaction that destroys the entire pack. To intercept this, a research team at the University of Arizona developed a machine learning model. They approached the heat problem by borrowing from weather forecasting frameworks that factor in time and location variables. Looking at this thermal array simulation, we can see the mechanism in action. By wrapping thermal sensors around the battery cells, they feed historical temperature data into the model to predict exactly when and where a hotspot will form. Once the software flags a future temperature spike, an automated safety switch cuts off electrical connections from the main pack. A potential explosion is safely downgraded to a routine maintenance alert. Expanding our perspective past the chassis, we arrive at the physical environment the car actually drives through. An electric vehicle's energy drain is heavily taxed by external forces. Wind direction and the severity of steep road inclines pull tremendous amounts of power. Researchers at the Arab Academy for Science designed a new GPS algorithm to calculate these invisible environmental variables in real time. This topographical map demonstrates the efficiency gains. By factoring in wind speeds and routing the car over flat terrain, the algorithm conserves roughly half of the battery's total capacity during a 50-kilometer journey. Optimizing the journey computationally produces the exact same result as installing a larger battery. Software extends the range without adding a single ounce of physical weight. Zooming out one final time, we connect to the global charging network. AI integrates the vehicle directly with the smart grid, monitoring battery health to schedule precise charging times that maximize driving range. Automakers like Volkswagen are already embedding generative AI into their dashboard systems, allowing drivers to seamlessly communicate with their cars to find and reroute to these optimal charging nodes. The compounding effect of all these efficiencies means future cars will rely on smaller power sources. Shedding that battery weight will directly reduce the immense physical stress placed on our global road infrastructure. The electric vehicle is outgrowing its origin as a static, heavy hardware product. It operates today as a highly adaptable digital platform. By systematically attacking the limits of chemistry, hardware, and environmental navigation, artificial intelligence is turning the physical obstacles of transportation into solvable data problems.